there's a lot of people hanging around, we'll just pick a different room. Probably the P-Chem closet. Okay, so last time we talked about the variational principle or the variational method, which tells us, hey, if we have a trial or a fake wave function and we want to know the energy of the system, the energy of that system will be at or above the actual energy. We're going to use some of those principles in talking about the chemical bond and solving for energies associated with molecules in a little bit. So the wave function of a molecule. So we're moving out of just multi-electron atoms and finally into a molecule. We're going to put a superscript molecule up there. Have sub I. What is the wave function of the molecule going to depend on? Yep, electrons, so R1, R2, dot, 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 and the position of those electrons. What else besides the electrons? Yeah, the nuclei. We're going to show their coordinates with a capital R, 2, and so on. Where R sub I is the position of which species? Yep. The ith electron. And R, big R sub I is what? Yep, position of the ith nuclei. Okay. There's a way to approximate this to get to an easier solution. Oppenheimer, that movie came out, what, earlier last year? So what is it, Robert J. Oppenheimer? Did anybody watch the movie or no? Yeah, okay. He's most well known for the Manhattan Project, but early on in his career, he helped develop an approximation called the Born-Oppenheimer approximation. Anybody know what the Born-Oppenheimer approximation says or stated? Yeah, the electrons move faster than the nuclei, and the electrons relatively are moving so quick that the nuclei just look like they're standing still in reference to the electrons. So the electrons move fast. And the nuclei essentially stay still. So when we look at the wave function of a molecule, we could approximate it as what? So what could we do to this, or how could we break it apart? Yep. So you have the wave function. We're going to put BO for Born-Oppenheimer, and then that depends on what? Yep, little r's, positions of electrons, and then we're going to have our nuclear wave function, which depends on the big R's. We'll hop back there in a second. Before we do, though, let's talk about the Hamiltonian. I'm going to write a bunch of terms out, and after I write those terms out, what I want you guys to do is pick them out and tell me, what are they? What do they represent? Okay? Yeah, it's important to develop the mathematics, but being able to look at the equation and tell what's actually going on is more important, I feel. Almost done. Okay. Does that look like a simple Hamiltonian? No. It's really complicated because there's a bunch of summations in there. It becomes really tough to solve. We want to try to make some approximations so we can solve this way easier, but before we go there, I want you to tell me what each of these terms is in relation to. So, this guy, what do you think it's for? It's kinetic energy, yep. What gives away that it's a kinetic energy? Yep, negative h bar squared over 2m, then we have a gradient. Okay, what's this the kinetic energy of? Yes. Why electrons, Lily? Yeah, we're not moving. Thanks to the Born-Oppenheimer approximation, we said the kinetic energy of the nuclei is equal to 0. Okay, what else do we got? This bit here. Okay, potential energy. Of what? Yep, nuclei and electrons. If you look, we got electron charge. What's this thing? Yep, charge of the nucleus. And we're talking about the distance between the electrons and that whatever nucleus we're looking at. This term, what's that? Yep. It's a potential energy. It's a repulsion between electrons. And then finally, this last term. Yep. Oh my God, how bad am I spelling potential? Is that even right? Yeah. Okay. Sorry, I'm like super sick from this weekend, so I'm like on a ton of Sudafed. I feel great, but I also feel really sweaty at the same time. It's great. Oops, I gave this away. What's this the repulsion of? You said it earlier. Yep. Okay. However, what would be nice is to have this represented just for the electron systems. So we can write a Hamiltonian. Which way do I want to do it? Yeah, I'll do it that way. Of just the electrons. What's that going to include? Yep, first three terms. Because that's where all the electrons are, right? Greater than I and N. Oops. Sorry. Can you say that one more time? This one? It will be negative once you include the charge of the electron in there. It should technically be, yeah, we can do it right at that way. If I pulled the negative to that point, it'd be the same. Okay. So this is what's known as the electronic Hamiltonian, which means there's a corresponding electronic wave function. So we have the electronic wave function. What's it going to spit out for us? Yep, the electronic energy it's called. And what else? Yep, the electronic wave function. So what's this thing? Yep, the electronic Hamiltonian. What's this thingy? Yep. The electronic wave function. And then what's this E again? Yeah. Okay, this is different than the actual energy of the system, right? Because what are we only accounting for here? We're only accounting for electrons. If we want total energy, which we're going to express as just E, some people like to put E total, is going to be our electronic energy. Plus, what else do we need, at least based upon our Hamiltonian, to get back there? Yeah, that last term. Oops. B. Okay, there's still an E squared, yeah. Just for solve. And in practice, this is just a string of constants that you have together based upon a distance, and you just plug that back in to get your total energy. So if you were ever really curious and you looked in your output of Gaussian, you would see electronic energy, nuclear energy, and then your total energy. That all gets factored in. Okay. So from here on, though, we're just going to use the electronic wave function. Because it's simpler. We've ditched some stuff out of our Hamiltonian. And it makes our lives a tad easier. Okay. But really, when we're concerned with molecules, what do we want to know about those molecules? Like if I have H2, what do you want to know about them? Yeah, how they interact. Is there a bond here or isn't there? So we seek have a qualitative, / semi-quantitative model of bonding. Wasn't sure if that was applause or someone dropping a bunch of stuff. Okay, to do that, we're going to look at a simple system. That's a diatomic molecule with atoms A and B. Okay. We start with the LCAO model. MO model. Have you guys ever talked about LCAO, or linear combination of atomic orbitals? No, that's okay. We'll explain what it means in a minute, but we're going to operate under a minimal basis. Where we just have one AO per atom. And the AOs are normalized. So if I were to consider the wave function of this molecule, we're going to have a function that corresponds to A, and another function that corresponds to B. So those could be the orbitals or the atomic orbitals. And then we have the contribution of A and the contribution of B. And these C's are just constants. They tell you the percentage that they contribute. Does that make sense? Okay. However, we want to know what these percentages are because that can tell us something. Like, for example, you could probably tell me what the coefficients are going to be for a system like this. What would those coefficients be? Given this is a purely covalent system. 0.5 for each of them, and that's exactly what you'd find. But let's say we want to find something a little more complicated like HF, then you'd have to go through what we're going to do next and utilize something called the secular determinant. Oops, wrong side. So what we need to do is we need to find the energy and we need to minimize it. We're going to be using the variational principle to do that. So we want the energy E, and it minimized. So we're going to use the variational principle. To do that, we want to look at the expectation value. So how did we denote an expectation value again? What symbols? Yep. Okay, and what does that mean? Yep, it's the average. How do we calculate it? Yep. Yep, so how do we get an energy? Yep, Hamiltonian, and we only care about the electronic Hamiltonian. And then what do we need on the other side? Yep, psi mole, d what? Yep. However, we don't know if this has been normalized or not. To normalize it, we need to do this. Okay. So now we can plug in for some of this stuff. What did we say our wave function's comprised of? This is technically the electronic that we're looking at. But how did we simplify our picture? We're going to use the LCAO model. So what does that mean our wave function is? Yeah, just this thing. So we're going to take that and plug that into here. Oops, I did it uppercase. All right. You can solve for this and you can get a value here. What we're going to do is we're going to introduce some shorthand. Where Hij is equal to this. And that's going to save us some time. We can get something actually meaningful in terms of the bonding now. This little bit right here, this is known as the overlap integral. And we're going to write a shorthand for it, SAB, like that. So we're going to draw a picture of it. And what this is it's a quantitative measure of the overlap of the atomic orbitals. How are we doing on time? 11? I don't think we're going to get there. We're going to have amplitude along here, and then we're going to have location. Say we have HA and HB here. So this is the location of the nuclei. If we look at the 1s orbital, what does the electron density look like for a 1s orbital? Or excuse me, what does the wave function look like? It's going to look something like this. Slater type orbital. Crap, I didn't make that big enough. Try that over again. That's terrible. Look, this little bit, the area underneath it, what is that? Yeah. That's the overlap integral. What has to be true about the value of SAB for there to be a bond? Yep, it's got to be greater than 0 for it to have a bond. Okay. But we still haven't figured out how to calculate E or how to get those coefficients. We now use the variational principle. To minimize E and solve for CA, CB. There's an algebraic way to do this, but we're just going to jump to the end. This results in what's known as the secular determinant. For our system, we need one of these terms for each possible linear combination. So what will the size of our determinant be, given we have two atoms? Yep, it's going to be a 2 by 2. So we get H. What's our subscript going to be for that one? Since we have A and B. Yep, both A's. What about over here? AB, SAB. Down here, what do we got? Yep, And then over in the bottom right. Yep. And what's this equal to? Yeah. Okay. So if you solve that, you get that information out. But we tend to write this in another shorthand way. SAA, what's the value of that going to be? If you look back at our little plot that we drew, it's A, an overlap of A on A. What will the value of that thing be? Yeah, it's 1. So really, that drops to be a 1, this drops to be a 1, and we're left over with some complicated stuff. Or another way to represent this, oops. It's like this, where this alpha of I is just equal to our Hamiltonian HII. And what would that be equal to? We wanted to express it out with wave functions. Yep. 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 This is known as the Coulombic integral. It tends to be negative, and it's the energy of the electron occupying the ith orbital. Beta ij. That's also equal to hij, which is equal to what? We want to write this in terms of wave functions. Yep. Then Hamiltonian, then what's on the other side? Yep. This is known as the resonance integral. In the case of bonding integrals, it's the strength of the overlap between orbitals I and j. It's negative for constructive overlap. What do you think it is for destructive overlap? Yeah, it's positive. And it's also sometimes called a stabilization energy. So it's the result overlap of I and j orbitals. It's negative, constructive, overlap, positive for destructive. It is often called the stabilization, or provides a stabilization energy. What's this thing got to be equal to again, this determinant? Yep. If you go back to our system, where we just had two orbitals interacting with one another, and a homonuclear atom, diatomic. What's true about alpha A and beta A? Or alpha B, alpha B? If they're the same atom, they're equal. Yep. So we're just going to call that alpha. You end up with two solutions. This is a bonding and anti-bonding orbital, where the energy is associated with them. Actually, we should be a little nicer and do our little epsilon. Okay. So really, what the attempt that we're trying to do, or what the programs all do, you have secular determinants and you're trying to find solutions to those, and they're a linear combination to try and solve those. There are different approximations that are taken to try and solve this, and one I would really like to explore is called Huckel theory, because you can get a lot from Huckel theory. Am I okay to erase this? So the whole point of this is to get the orbital energies and to get those coefficients associated with those, so we can understand the orbital overlap and get an idea about the bonding of our systems. Okay. So let's talk about Huckel theory. So this is a way to solve for a multi-electron, multi-atom system. What are we going to need to solve for this? We're going to have to make some what? We're going to have to make some determinants. We're going to make some secular determinants, and we're also going to conduct some approximations to make solving those easier. The overlap integrals. What symbol did we say those give those? Yep, SAB. We're going to take the simplest scenario. What would you set that to make it simple? 0 is simpler than 1. 0. All resonance integrals. What symbol did we give for the resonance integrals? Not alpha, but beta. Between non-neighboring atoms is equal to 0. All neighboring beta are set equal. Are these good approximations? No, they're terrible. What they're saying is atomic orbitals don't overlap. The whole idea is to get an idea about bonding. How does that help us? Well, back before computers were fast enough, people actually had to solve this stuff by hand, and you can get some useful pictures out of it. Actually, many pictures you've seen in your textbooks or have even utilized themselves. So what we're going to do is we're going to consider the pi system for ethylene. Okay, what does ethylene look like again? 2 carbons. What's between them? Yeah. How many pi electrons does this system have? 2. If we were to write out a wave function for the pi system, it's going to be comprised of what? What make that pi system up? 2 carbons, specifically what on those 2 carbons? Yeah. What is the hybridization of this carbon? sp2, yep. So where? Yes, the p orbital. We're going to call it the pz orbital that's not being hybridized. C2pz. On carbon number 1. C2pz on carbon number 2. And there's some coefficient there. Okay. We need to make a secular determinant. Okay, our secular determinant, what's it going to look like? We got alpha. Nope, it's okay. Alpha. Yep, 1, 1 minus our energy, right? I'm going to give it a capital E. Then we got beta minus ES. Then we got beta minus ES. Alpha minus minus E. Okay, and then we got 2, 2. What about for these betas and S's? Yeah, 1, 2, 1, 2. It doesn't really matter their order. And what's that all equal to? Now, Huckel approximations. SAB, what's it set to? 0. Okay? So what's going to change in here? Those go away. What else has changed? These two are right next to one another, so that second one, nothing really changes there. Yep. The betas are equal to one another, and we don't have to worry about these labels. So after we end up with alpha minus E, beta, beta, alpha minus E. And that's all equal to what? Yep. If you solve for this, you should get 2 roots. Energy is equal to alpha plus beta, or energy is equal to alpha minus beta. Okay. What we're representing here is, what was it? Negative value, bonding, and anti-bonding contributions. So, if you represent this graphically, you got your 2 p orbitals, and they overlap that way. Oops, 1 electron in each of those atoms. We're talking about that MO, and what's the anti-bonding one going to look like? Yep. Okay. I know we're at the end of time, but I want to talk about one other thing really, really fast. Let's say we had this system. Three carbons, we're going to do the same thing. What size will our determinant be? Yep, 3. Okay. Along the diagonal, we have this. Now we got to look at adjacent carbons, and that's where we have betas. So between carbon number 1 and carbon number 2, what should this term be? Yep. What about this guy? Yep. What about between carbon number 1 and carbon number 3? 0. Because there's no overlap between them. We said non-adjacent ones. What about 3 and 1 then? Yep. What goes in these terms? Yep. And what's this whole thing equal to? Okay. If you know how to set that up, that's the most important part. Solving it can be a little complicated, so check out those YouTube videos on how to solve it. One of your daily problems is coming up with solutions for these things. Okay? I know that was a metric shit ton of information being crammed into your heads. If you have questions about it, come talk to me about it. Try to review those videos. I know there's a bunch of stuff that's going on, but for the ACS, just know how to set up these secular determinants. Okay? Are there any questions? I know you got to run, Owen. Sorry.